Ready again? Good. Then next is stochastic differential equations. This is now formalizing our Langevin approach to things that also contain what's called multiplicative noise, and you'll see what it means. I had a comment on this just before the break. These stochastic differential equations are quite important, not just in physics, also in finance, and I guess you will calculate a nice exercise that deals with the Black-Scholes equation. So let's start, and let's start very simple. So let's say we have just a process for a one-dimensional variable, which has just noise, just white noise. So as we had it, psi of t prime is 2d delta of t minus t prime. Mean is 0 as usual, and now let's write this in an incremental form. So let's say I want to know x of t plus delta t. Well, for that you have to integrate this equation from t to t plus delta t, and then you get x of t plus delta t minus x of t. We'll write this x of t on the right-hand side. And additionally, you get the integral of the noise over the time interval between t and t plus delta t d tau. All right, and that object over psi of t, and that object here I call delta w of t, and this is known as Wiener's increment in the analysis of stochastic differential equations. Pardon? Yeah, sorry. I'm going to mess this up often, I'm afraid. But thanks for correcting me. So that's what this equation is. And this is a proper form that you would like to study, because now you think of this as incrementing your way forward in a way you would solve a differential equation. In a differential equation without the noise, it's very straightforward, because you just increment the derivatives, and you can do different schemes, Euler scheme and whatnot, but that's a standard way of solving a differential equation. The additional complication that comes in incrementing a stochastic differential equation is that you not only have these deterministic increments, you also have increments called the Wiener increments that are stochastic variables. I need to worry about what this means, what these stochastic increments mean. All right, so let's then do the analysis in this form. So let's solve the Langevin equation by using this discretized form. We know, and you can do the math for yourself, if you take the delta w, square it, take the average, use the correlation function for the noise, then you get for the increment something that looks much nicer. It has no delta functions anymore, but it is proportional to delta t. And here you see the dilemma, right? The delta w average, a squared average, is delta t. So that means you expect that the delta w scales as square root of t, of delta t. All right. And we know what the probability distribution function is. So it's a Gaussian. Because all that we've done is to integrate it. So we have a sum of Gaussians, and the sum of Gaussians is a Gaussian. So that means the delta w also must be a Gaussian distribution with the variance defined by the second moment, as we have just calculated it. So it's delta w squared of t divided by 2d delta t and a minus. Okay, to be precise, I always mean here delta w squared. I'm just writing this in a more handy form. So that's what you have when you go to the incremental form. And now we go along in the calculation as we did before. We consider a time interval and then look at trajectories on this time interval where we do have times tk equal to k times delta t for k from 0 up to a maximum number of indices. And we then define the delta w k as the delta w's, where I take here the time at tk and at tk plus delta t. So that by definition is then the integral from to tk plus 1, which is tk plus delta t, d tau psi of tau. And we also make it such that x of 0 is chosen to be 0. If you have that, then the equation for x is just a recursion relation. You start from x0 to 0 and you add up all these random variables. So that means that our x of t that we have is nothing but now the limit of infinite number of time points from 0 to n minus 1 delta w of k. So this is the integral from 0 to t of dws, and that's the definition of this, and that I call w of t. Okay, with that, we have expressed the stochastic process in terms of these Wiener increments as a stochastic integral, and that's the first time you now see such an object. It's an integral defined by the left-hand side over this discrete sum over a differential that's a differential of the Wiener increment. It's not a usual type of integral that you know from calculus. It's one that comes in here because we have stochastic variables. Okay. Now we do have that these delta wk's, they are IID and Gaussian. Then I can do the calculation of moments. So for example, I can calculate the second moment. Well, for that you just need the expression that I've defined here. Or maybe call this here x of Tn. Then we just insert here the corresponding values for the Wiener increments from 0 to n minus 1. And I take the average, where I have to take now the average of the squares. Okay. Using that they're independent, that's why I can neglect the terms with different coefficients. Well, and that is the limit of n going to infinity. I do have from each of these delta wk's, as I wrote it here, 2d times delta t. Right? And we also have here, because of the number of terms here, we have n terms that appear in that sum. But in n times delta t is t, so this is 2 dt. Okay. Now I have this p, I have the x. I know it's a sum of Gaussian variables. I know its second moment. I'm done. I know this is a Gaussian distribution. Okay. So we have then p of x and t being a Gaussian distribution 4 pi dt exponent of minus x squared over 4 dt. Okay, it's not really a surprise. I'm just getting the same result I got before in very different ways, with yet another way. And I wanted to show it to you because it gives you a path of solving a stochastic differential equation, and it highlights that along the way of solving a stochastic differential equation, you need to define a stochastic integral. Good. Now let's go to what I call our first version of Ito's lemma. In a very simplified form. And that's instructive because later on it may seem more formal. Here this shows you really the core of the Ito lemma in a go. So let's, for that, and it's about random variables, and it's about how they converge if you take many intermediate steps. So let's define this variable y of t, which is this sum from k equals 0 to n minus 1 delta w k squared. It's also a stochastic integral because it's a sum here over the second moments of the delta w's. And we want to know what the value of that is. We can do the mean, y of t. Well, that's very easy. This is the sum from k equals 0 to n minus 1. I've done this just a second ago. Delta w k squared. That's sum over k equals 0 to n minus 1 delta t, and here for simplicity of making my life easy in terms of notation, I put d equal to a half, so I get just t. Writing this as an integral means that the integral from 0 to t delta w of s squared average is equal to time. So that's the average of a integral object with a differential that's the variance of this Wiener increment. What I'm telling you now is that you can actually take away the brackets. If you consider this in this limit of n going to infinity, then this is an exact value. Not just on average, really an exact value. And then you see, now I have something where I can do an integral with a definite outcome instead of a random variable as an outcome. Let me show you that on the slide. So you see how this plays out. Oh. Computer just died. So I'll draw it here with my limited drawing abilities on the board. So let's say I draw two things here. I draw on the board my random variable, which is the sum of the delta w k squareds. And here I have time. And I'm now taking 20 points along the time discretization. And I evaluate this stochastic variable many times by choosing the corresponding values from a Gaussian distribution. And what you will get is something like this. A very broad distribution of values. If you increase n to 2000, and you may try this on your own, you basically get that. All the trajectories fall on a single line. Well, why is that so? Let me show it to you. It means, right, if you look here, then the variance that you have of these trajectories for that random variable, that variance goes to 0. And that's what I'm going to show you next. So let's look at the variance of our random variable, which is the limit of discretization points being an infinite number, and the variance then of the discrete sum from k equals 0 to n minus 1 delta w squared. It's a variance of a sum, and each element there is from a random variable that's Gaussian. And then you know this variance of a sum is a sum of variances of the same thing. So because this is Gaussian, the limit of n going to infinity of the sum from k equals 0 to n minus 1 delta, the variance of delta w k squared.
Yeah. Delta w a Gaussian variable? And
yeah.
Delta w squared is the square of a Gaussian. That's not a Gaussian anymore.
Delta wk is the Gaussian variable.
Yes.
And then these things are true for all objects that you construct with Gaussian variables.
But the square of a Gaussian is not a Gaussian anymore, but the variance still adds.
The variance of these objects still has that property. Okay. Now, in the end, you do have now to calculate something like delta w k to the fourth, right? And you have to subtract delta w squared because that's how the variance is defined. So minus delta w k squared. So here, to evaluate a higher order Gaussian, you either do it by hand and calculate it, or you know Wick's theorem. And Wick's theorem tells you that you have to sum over all possible contractions. So that means this here, you can do 3 contractions. That's 3 times delta w k squared average minus delta w k squared. Okay? So in total, you get 2 times delta w k squared. So this is then the limit of n going to infinity, sum over all our discrete time points. And I have then 2 times. And the average of delta w k squared is again what? Delta t. So 2 times delta t. But now I have to square it, because I have the square of delta w k squared. Well, and then as you insert what we do have in our discretization scheme, n going to infinity, this is n times the same things, times 2, And then delta t is t over n squared. Well, and then you see this scales like 1 over n, so it goes to 0. That proves the point. So in the sense of deviating, of the variance going to 0, this integral converges to t. Okay, this is the mean square limit is this, and this means this is ds from 0 to t. And that is my simplified version of Ito's lemma. So it's a deterministic result in the mean square limit for a stochastic integral. Questions? Good. Now that we are ready, knowing what stochastic integrals are, we discuss Langevin equations with multiplicative noise. So what I mean by that is the following structure. You have, again, for simplicity, a one-component random variable, x of t. I do have a drift term, as usual. We had this, x of t. But now I'm saying that the noise term also depends on position. So I'll write here a function c of x and t times lambda of t, with lambda average being 0 and lambda of t and t prime having unit variance. So that is delta t minus t prime. That means I still have Gaussian white noise as an amplitude, but the amplitude has a dependence on configurations. This appears in finances, this appears in population dynamics, and it appears quite in general in all kinds of problems where you couple the noise to the population itself, and that's quite a standard case. Okay, so this is what it means to have multiplicative noise, because this multiplies the white noise term that you have. Okay, now let's be naive, and let's say we do calculus as we know it, meaning we just juggle with differential as we like them. So let's say I write this, so put it here, naive calculation. I write x dot, and I divide it by c of x. Then the right-hand side will be a of x divided by c of x plus lambda. So I'm back to a additive noise, and I define now a new variable which I call dy, and that's accounting for the fact that I have this denominator c of x. And I also define a tilde of this new variable y as a of x divided by c of x, and y and x related by this parameter substitution. Well, if you do that, you are back to the ordinary differential equation. Okay. So that means then we have transferred it back to additive noise for a dynamics for y point. And that means we have a solution. Okay. So from that, we know that we can construct a solution, py of t, which is c of x, p of x and t. And the c of x appears here because I need to account for the Jacobian of the transformation, and I need the c of x here such that p of y is properly normalized if p of x is normalized. And the Langevin equation, just to be explicit, for dy dt is a tilde of y of t plus lambda of t. And the corresponding Fokker-Planck equation, dt p tilde of y and t is minus dy a tilde of y, p tilde of y and t, plus a half dy squared p tilde of y and t. Because we know that Langevin equations are equivalent to Fokker-Planck equations, so I'm there. Now we transform back to our original variable x, and then you get the corresponding Fokker-Planck equation for x. There's a few steps of algebra which are not hard. I'm just giving you the result. This is minus dx a of x plus a half c of x, c prime of x, p of x and t, plus a half dx squared c squared of x, p of x and t. You can also write this in a different form by shifting this term here to the right. And this looks like a of x, p of x and t, plus a half dx c of x dx c of x p of x and t. So you can do it if you're naive and can calculate the Fokker-Planck equation that corresponds to one with multiplicative noise. And now let's compare a bit of what this means. So you start out from a Langevin equation that contains that, which, if this were to be a constant, is just a diffusion coefficient here, up to a factor of 2, but that's what it is. So you would get a Fokker-Planck equation where on the right-hand side you would have a d on the right-hand side. You don't quite have a d here on the right-hand side. You have a d of x. And you see this d of x is somehow sandwiched between the differential operators. You have half of it before the first, next to the first derivative, and half of it next to the second derivative. And that's just what you get by naive calculation. Question is this here right? Or under what condition is this naive calculation correct? Yeah?
If the c was a constant, wouldn't the second term also be 0? Because we... no, sorry.
Mm-hmm. Then you can pull it out.
Yes.
So if c is a constant, you can pull all of this out and it's a factor in front. Okay. So is this right? Under what conditions is that right? And again, to deal with that, and that's why I had this preamble on this very simple stochastic differential equation, you have to seriously go from a differential equation in time with continuous time to something where you increment the time, and you have to seriously consider what you mean then by the stochastic term on the right-hand side. Okay, so let's go there. Let's go to stochastic integrals. Then dxt, right, the differential, meaning this difference here, has a term which is a of xt t dt. That is just the deterministic solution of a differential equation written in terms of differentials. Differential of x is the drift term times dt. But now, when you look at the second term, you have plus c of xt t dw of t. Wait a second. Okay. So those are functions which are bounded, a and c. And for this increment, I'll take that this is a Gaussian variable, 2 pi dt, exponent minus the wt squared divided by 2 dt. So that's my definition of a stochastic differential equation with multiplicative noise in terms of increments instead of differentials. Let me add here that this, of course, implies that this object has 0 mean, and the increments have a variance that's dt. Good, and now we can again try and integrate. So as I integrate this, I get the initial value of this, and to be precise, this is at time t0. Then I integrate from t0 to t over tau a of x tau comma tau. And this is all standard. That's how you would integrate an ordinary differential equation. And here you also have an integral from t0 to t. But now the integral is over this differential increment that is a random variable. And we have to define what we mean by that. So let me draw this and then show you what the choices are. So here we have time. Here we have also time. And now I'm choosing here certain time points, t0, t1, t2. And maybe I just continue here with time. Here I have then at some point tn minus 1 and tn. That's my axis. and it will have some kind of trajectory, which I'm not drawing random, but as a continuous function. But I guess you forgive me for that. This is some trajectory that you may find, and there are many of those trajectories that you can have. Okay. Now, let's say we have a function g of tau, which is arbitrary, and we want to define t naught t d tau, dw tau, g of tau. We can do this by a limiting procedure, right? We can say this is a limit of n going to infinity, sum from I equal 1 through n, but now it's not really fully clear what you do. Where do you choose the taus here to be? You can say, well, let's choose the g here at some points I call ti bar, and the w's here at the time points that I indicated, and the ti bar are just some intermediate values that you can choose here. Here, some t 1 bar, and here some t2 bar, etc., up to here, where you choose some tn bar. That's a way to define the stochastic integral, and I do have that choice. I don't have to pick the time points here at exactly the same points. I can make it different. Just take it as a definition now, right? I'm saying this is a definition of my Langevin dynamics, and this is the definition of the corresponding stochastic integral that you get by solving this stochastic differential equation. Whether that is related to a concrete physics problem or biology problem or finance problem depends on reality, so you have to match whatever the reality of the process is to the math that you have here. Now we just have a definition of what we consider to be a Langevin equation in this differential formulation. Yeah, and this delta w, I have to define this. This delta w of I is w of t of I minus w of ti minus 1. Okay, there's two different integrals I can define. One is the Ito integral. There I'm saying that I'm choosing my intermediate points in this calculation such that I'm defining this to be the limit summing over all the time points, and I'm choosing the function at ti minus 1 delta wi. So before the increment at time ti minus 1. So before I increment my random variable. So this will not depend on this random variable. Just think of this trajectory here as it unfolds. It will take some values, and you have to, at each time point, choose another increment to forward the trajectory. The trajectory you find at time ti minus 1 is independent of what you choose next as your Gaussian increment. So these two things are statistically independent by construction of this Ito integral. The Stratonovich case is taking the same thing, and you take the limit of n to infinity, the same sum from I equal 1 through n, and then the choice is that you put yourself right in between those two points. So that's a half ti plus ti minus 1 times the Wiener increments that we have. What we do next is now we calculate, and I'm not going to do this before this afternoon, we're going to calculate what the corresponding equations are. And for that, I just leave you with this. For the Ito choice, you can increment it like so. You have A of xi and ti times delta ti plus c of xi ti times delta wi plus 1. And we will then use that relation that we have for Ito, and I'll show you then in the afternoon how from that equation you then derive a Fokker-Planck equation and what kind of Fokker-Planck equation we get. As a spoiler, this will not give you the same Fokker-Planck equation as the one that we did naively. The one we get naively, you have to do this Stratonovich choice, and then you get the naive calculation being, quote, quote, the right calculation. Good. With that, let's break, and then we have another lecture this afternoon at 2:15. Same room.